Hi. Welcome to Calculus 1, the second part of the class where we talk about linear approximation and differentials. Let's see. So this section is one of the sections that honors the ancestors, I guess, because I would say that this really lost its bang today because of the all the software we have, Mathematica, MATLAB, Maple, and so on. Linear approximation is used to take this. I mean, for calculation, there are other things in mathematics that this is still relevant to, but not for calculation. So this was used to take difficult problems that are difficult to calculate and make them easier to compute. Now, what I love about this section in particular is to use it and deal with people who go, what do you know? Well, I know how to find ln of 3 by hand, or square root of 5. What do you know? Right? So, you can use it for that. What is linearization? Linearization is when you have a function which is nonlinear, sine x or tangent x or e to the x, and using calculation, it's actually tangent line, you change that equation into a linear equation which is easy to compute. So to give you immediate, and then we'll do calculations, to give you immediate use, say that you have function y equals sine x. You know that that function is a sine wave that looks like this. But then, this is a line y equals x. And you see that in this region here, right, for small angles, sine x is approximately the same as x. The values, they match. So in applications in physics and engineering and so on, you can replace sine x with x and have much easier calculation. So that's technically a use for this today, but it had much larger and more important use long time ago where calculators did not exist. And that is to actually find values for, as I said, ln2, ln3, ln4, square root of 16.3, and so on. So you can actually compute anything using these techniques. And what this is actually just figuring out the tangent line at the convenient close point. So I would like to demonstrate these ancient techniques by figuring out the square root of, let's find square root of 10. We can figure out square root of 10. All right, so if I want to find square root of 10, I first define a function as square root of x. I know that the square root of 9 is 3. 9 is close to 10. That observation is key for our success. So the goal of this problem is to compute square root of 10 by hand. And you are looking at the square root function. And you are looking at the closest value to 10 that you can do by hand. In this case, it's 9. So what I'm going to do is I'm going to find a tangent line to this function at 9 and I will compute 10 in the tangent line instead of in the function. Now, what does this mean? Well, first let me draw a diagram, a graph. This is a square root function, and let's say this is over here is 9, which means that's 3. But I want to compute 10, which is here, which is a little bit more than 3. But observe what's happening here. If I am to draw a tangent line at 9, you see that y values at 10 for tangent line and for square root are not the same, but they're pretty damn close. So I am able to calculate everything easily for 9, and then once I have the tangent line, I can just plug in 10. So let's find tangent line at 9. For tangent line, we know we have to find the slope by doing the derivative. So f prime of x is 1 over 2 root x. And the slope m is 1 over 2 square root of 9, which is 1 over 6. So now I have a point 93, and a slope of 1 over 6. I can find b quickly. So y is equal to, mx plus b. Let's write the formula. So y, which is 3, is equal to 1 over 6 times 9 plus b. So that's going to be 3 equal to 3 halves plus b. So b is 3 halves. Y equals 1 over 6x plus 3 halves. This is the tangent line. I don't know why I boxed it. That's the tangent line at x equals to 9. I'm going to use this to compute. So square root of 10 is going to be approximated by plugging in 10 into the tangent line. So that's what? That's 5 thirds, right? Plus 3 halves. That's 6, so 10 plus 9 over 6, 19 over 6. What happened? Oh, 19, yes. 19 over 6. So my claim is the square root of 10 is close to 19 over 6. Now you can actually take the stick and divide that in the sand, you know, we don't even need paper. 19 divided by 6, you can see that's 18, like so 3 and 1/6, right? So 3 and 1/6, which is 0.12. Yeah. Well, it's 3.16, right? Yeah. 3.16666 forever. Going on. So now I'm going to actually take the square root using the calculator to just verify. So square root of 10. So this is what calculator gives. 3.16227766. That's all decimals that my calculator displayed for square root of 10. And we calculated by hand, without doing any work with the calculator, not even calculations, to get 3.16666. That's pretty damn good, right? If you round, you are 1 cent off. No one cares, right? So you can use this technique to compute tangent of 12 degrees, to compute ln of 3. Let's compute ln of 3 because we can. So how much is ln of 3? You have the technique. Define the function. What will be the function? ln x. Good. What is the cool value that you know close to 3 that you can compute by hand?
1.
Close to it. Yeah. Yeah. What is it? E. 2.7, right? I know. All right. So find the tangent line at E.
Today, please, one.
Okay.
One of my professors actually got upset that that people sneezed and then people said bless you. And he's like, all right, well, we're gonna bless the whole class for the rest of the semester.
I'm bored.
Yes, yes, yes. But
Oh, like this type of thing.
No.
That has all pictures. That has a phone.
take the pictures off.
Yeah.
Put them back.
Take all the pictures off. That just give you a little bit. No, I take it back.
Okay, so the associated function is ln
It's
x.
just the dog.
The cool value we know is that ln of e is 1. So the point is e comma 1. To find the tangent line, we will find the first derivative, and the first derivative is 1 over x, which means that the slope is 1 over e. Cool. We will plug that into y equal mx plus b, and get that y, so y is 1, is equal to 1 over e times e plus b. So b is 0, right? E and e cancel, you get 1 equals 1 plus b, so b is 0. And we get that the tangent line that approximates is 1 over e times x. That's the tangent line. So now that I have the tangent line, I will compute number 3 in the tangent line. So y, let me just do it this way actually. ln 3 is approximated by 1 over e times 3, which is 3 over e. Now e is about 2.7. We are approximating everything, so it's okay to put 2.7, which is 30 over 27, right? 30 over 27. When you cancel by 3, you get 10 over 9, which is approximately 1.111 forever. Now let's calculate ln 3 in the calculator. So calculator gives me for ln 3 1.098612289, and we got 1.111111111. So if you round this to 2 decimals, let's say money, right? 2 decimals, we are again 1 cent off, right? Because it will round to 1 and 10 cents. So you see how close these things are. And you can literally compute anything with this. Anything. You just need to find that close value that you can compute by hand. When I had to, do a square root of 125, remember we had that in earlier calculations, square root of 125? I knew it was 11 point something little, right? Because the square root of 11 is 121. Sorry, square root of 121 is 11. That means that the square root of 125 has to be 11 point, just a little piece. So what is linear approximation? Linear approximation is figuring out the tangent line at the close point that you can easily compute. And you compute your evil value, if you want to call it that way, in a tangent line, but tangent line is a linear line. So what do? You just add and subtract and multiply basic operations, right? So now we are going to write this awesome one-liner for tangent lines. Linearization of x is equal to f of a plus f prime at a times x minus a. This over here is called linearization equation, but it's also a tangent line equation at the same time. So this is linearization. But at the same time, it's a tangent line thing. All of the things that you used to figure out in little chunks, right? You first find the derivative, then you plug in value to find the actual m, then you find the y value for the problem, then you plug all of those things in to figure out b, and you have the tangent line. Well, now all of that is done in one shot by plugging everything into this equation. So let's find I don't know, what else could we calculate? Do you have any wish or anything that ln square root? So how about we do a trig function? We haven't done any of the trig. So how about well, that's cool. That's a function, 8x, right? So maybe secant of I don't know, 1.8. How about secant of 1.8? Actually,
3.
Well, you have to plug in the value. See, if it's 1.8, are you using degrees or radians? Radians, right? Secant of 3 radians.
Yeah.
Okay, so how much is a secant of 3? Secant of 3. Now, secant of 3, that 3 is in radians. I have to say that, right? All right. Well, 3 radians is close to pi. So what I know is secant of pi. Secant of pi is 1 over cosine of pi. Cosine of pi is, very good. So the whole thing is -1, and I have a pair pi -1. So that's my value, pi -1. So now what I'm going to do is I'm going to, I wanted to say that A, to use the formula above, we have that the function f of x is secant x, and A is equal to pi. That's the only thing you need to plug in the equation above. So what is the linearization L of x? It is secant of pi minus the derivative of secant is secant x tangent x, but we have to plug in pi's there, times x minus pi. So secant of pi, we know it's -1, minus secant of pi is -1, and tangent of pi is 0, right? Times x minus pi. So the whole thing is -1. This is linearized by this. Wow. I don't like this. I don't like this, but such is life. So, oh yeah, but this is so close to negative. That's why it's so close to -1, because it's close to pi. So -1. We actually see that right away. This problem didn't work out that nice, but we do have answer, right? We get -1, so secant of 3 is approximately -1. All right, this was not the greatest example. Let's do something with the square root. It's gonna work out much nicer. Do we want the cube root? You want a cube root? Okay, let's find the cube root of 9. Cube root of 9. So what's the cool value? 8. So f of x is equal to cube root of x, and a equals 8. The derivative is going to be what? X to the, well, it's going to be divided by 3, right? It's -2/3, right? So it's 1 over 3x to the 2/3. That's it. Awesome. So what's the, let me write the linearization. It's going to be f of a plus f prime of a x minus a, and I'm just going to plug everything in. So L of x, f of a is cube root of 8 plus the derivative computed at 8, which is this, and then x minus 8. And now simplify. 2 plus 1 over 12 x minus 8 cube root of 8. So these 2/3, right? It has 2/3, so a third is the cube root of 8, which is 2. Square that is 4, times 3 in front is 12. So linearization is 2 plus x over 12 minus 8 over 12. 8 over 12 cancels down to by 4, right? By to 2/3. And then I have 4/3 when I combine it with 2. So Lx is equal to x over 12 plus 4 over 3. This is the linearization function. And I want to compute 9, right? So the cube root of 9 is going to be approximated by computing L at 9, which is 9 over 12 plus 4/3, cancel by 3, 3/4 plus 4/3. That's going to be 12, 9 plus 16, 25 over 12. Now 25 over 12, that's like 2 point, and then you have 1 over 12, so I would say about 0.9, just to approximate. And let me find the cube root now. So that's gonna be 9 raised to the open parenthesis 1 divided by 3. I hope all of this is good. Yep. So our calculation worked out to be about 2.09, and the calculator is giving me 2.08008. We are again 1 cent off on the calculation. You found the cube root of 9 by hand. We didn't use calculator anywhere. Yes?
If you didn't like factor the 1/12, would it be easier to solve?
What do you mean?
Like you didn't distribute it, come in?
Oh yeah. I mean, you can leave it in this form, and then 9 minus 8 is 1. So 2 plus 12, right? Sure. But I like to see this line here, because that is the tangent line, actually. If you are to find tangent line, you will have that as y equals, and it will be the same equation. All of this, guys, will become more interesting and more developed in Calculus 2 when we do power series, you do Taylor expansion and so on. It will become much more powerful tool. So what have I done so far with linear approximation? I approximated the value. So ln of 3, cube root of 9, square root of whatever we calculated. So I computed those values. And you see that you can either find the tangent line using the methods you know from your previous life, or you can memorize the new formula, which is tangent line in disguise, right, giving it some kind of one-line formula. Cool. The second part of the lecture is differentials. These guys approximate the change. So differentials approximate change, where linearization approximated values. Maybe I should add that somewhere. A linear approximation. I don't know if I... Here, I can do linearization, approximate values. So Differentials will approximate change. It is very easy to derive the formula for differentials just by manipulating terms. You know how you say in pre-calculus that y is equal to f of x. When you differentiate this, you will get dy over dx is equal to f prime of x. We haven't done much, right? And then dy is equal to f prime of x dx. And there's your formula for differential. That's the differential. So variables are separated. You have all the x's on the right and a y on the left. Now, what does this stuff mean? Well, first of all, what is the change? Change is when you look at the triangle, let's say, let's not look at the triangle, let's just say that the change in x is x2 minus x1, and change in y is y2 minus y1. Now I can go to triangle. If I draw a triangle and label 2 points, this is your delta y, this is your delta x. The slope that you know from your algebra, m, is change in y divided by change in x. That looks awfully the same as our derivative dy over dx, right? So, we will say that delta x is the same as dx. That's important thing. And we will also say that dy is approximately dy. That's why things work. So, I can use the formula dy equals f prime of x dx, which can also be understood as f prime of x delta x, right? Because dx and delta x is the same thing. I can use it to approximate, so use it to approximate change. Now the fun part is that I can actually use this stuff to compute the same problems and same values like we did with linearization, just in a different way. I can use this to find ln2, ln3, ln5. I can use this to find sine of, 17 degrees. I can use this to find technically anything, because I'm not going to compute the value. I'm going to compute the change in value and then add that to the value. So let me give you an example of that use that we don't use anymore. So let's say you want to compute a square root of, I don't know, how about 85? Doesn't really matter. So how much is the square root of 85? Yes, you can go and do linearization, but let's use this new method. F of x is going to be what? Very good. And now this is what I'm going to do. I'm going to say easy value to compute is 81, and I need that to change to 85, right? So I have my delta x to be 85 minus 81, which is positive 4. Do we all see that? So this is where change happened. I pick a value that I can compute, and I say the change of that value into 85. Now I'll explain, from the other perspective when we do word problems, which are relevant for engineering and stuff that we do today. But I just want to get over with the simple calculation. So I have this. And now, all I need to do is to say that the change in y is approximated by dy, which is equal to f prime at a times 4, right? So f prime of x is 1 over 2 root x. So f prime at 81 is 1 over 2 root 81, which is 9, which is 18 altogether. So what I found is that the dy is equal to 1 over 18 times 4, which is 2/9. Now, I'm going to write this in blood over here. This is change from change between BTW between square root of 81 and square root of 85. So I hope it's clear and it's common sense to say that square root of 85 will be approximated by square root of 81 plus this dy change. So that's 9 plus 2 over 9, which is about 9.2222 forever. Let me find the square root of 85 in the calculator. Nine 9.219544457. This is all the decimals that we get. So if you are working on linearization, linearization is going to take the square root of 85 and calculate that directly into this number. What differentials do is they approximate the difference, right? The difference, the change between square root of 81, which you know, and the square root of 85, which you don't know and want to know. So see, we calculated the differential, which is the difference between the two things. And then you add that difference to the easy one to come up with the value. So it's kind of indirect way. Instead of calculating the value, you calculate the change, you add it to what you know to come up with what you want to know. Or you just take the calculator and get stuff, you know, Mathematica or something, and get as many decimals as you need / want. That's not what we use this for today. What we use differentials today for is for serious engineering stuff, application. I will give you a few examples, but technically anything you build has differential worked in somehow, somewhere. Let's take a train ride, our mental train ride anywhere, and you're sitting on a train and you hear tick 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 tick. You hear it so much that you actually filter it out very quickly and you stop hearing it, but it's always there, it's persistent. You hear it more during the winter than during the summer. Why is it there? What does it do? How does it, where's that sound coming from? It's obviously train tracks and the wheels, right? You have the metal wheels on the metal train tracks, and that's what makes the noise. Now, where does the noise come from? You have a train track like this, then it ends, and the next one begins, right? This is where those wooden planks are, right? Underneath. And there's this gap. Why is there a gap there? What happens with objects when they are introduced to heat? They expand. Now, being that the train tracks are nearly linear, right? It's just a, you know, whatever amount of feet, yard long. They're going to expand in length a lot, but they're not going to expand in width a lot, right? So during the summer, they expand and these gaps nearly close. In the winter, it's cold, they shrink and these gaps open a lot, right? They don't open enough for train to derail, but they open enough so this sound, tuck, 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 tuck. And why is it so tuck, 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 right? It's always the train has the two wheels, right? And then a two wheels. So every time when the pair goes over it, it's tuck, 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 tuck. And then wait for the next pair. So next time you're on a train, pay attention to that. Now, there are engineering formulas that are designed, right? So these are the train things. You have the shocks and all that stuff. The design of these rails has to be done in such a way so that when they expand, they don't push on each other and then bend. And you can actually find images online from, you know, hundreds of years ago when people didn't take this into account, and then they built the rail and then the rails just pop up. Another application would be bridges. You know, when you drive over a bridge, right? So train. Oops. So bridge now. You know when you drive and you have the crack in a bridge. Right? You've seen these. They're on, you drive over these, right? They look like that. Same purpose like the train. Over the summer, bridge will expand and those will close. Over the winter, they would have 2-3 inch separation there, or 4. So bridges have that, large bridges have that incorporated in their design. You have to, otherwise the bridge is just going to rip to shreds. If you leave it over the winter, it's just going to collapse. Do you guys still know what the CDs are? CDs. It's a disc. They used to put music on that. All right. Yeah, and you used to carry that with you, put it in a car. Cars used, or a Discman. Yeah,
You used
yeah.
to make CDs for people.
Yeah, you used to make, yeah. Used to be, well, in ancient times, it used to be a mixtape, right? And then you use the mixed disc, and today you just don't do anything because that's it. Oh yeah, you buy people iPad with music on it, right?
Well, music is already free now, so.
So, oh, actually, wait, their Blu-ray today is the thing, so we can talk about that. Here, DVD. You hopefully know what that is. So, well, I have to be mindful of the generation, right? Because it's digital, right? I have Netflix. I don't need any of this nonsense. So, DVD. Does anyone know how DVD works? What's just nutshell?
Isn't it like a little small beam that like...
Laser beam, very good, which shines onto a disk, reads off the data, that gets processed. Right? Very good. What happens when you shine a laser on something?
Reflect?
Huh?
What?
Yeah, his voice is gone. What happens when you shine the laser onto something? Let's not talk about physics of how it reads the data. What happens with the actual disk? Don't worry about the rays, don't worry about the data, don't worry about what happens to the disk when you take it out.
It plays the movie.
It's warm, thank you. The laser will heat the disk and it will heat it a lot, okay? The damn thing is spinning on 10,000 of RPMs right inside. And then, yeah, it's spinning really fast. And it has laser pointed at it. The damn thing is going to heat up. And then do what? Expand. So now you have a disk that is spinning at some angular velocity. But then you have a linear track on which you have this head that moves linearly back and forth to read the data. So if the disk becomes hot and you are not compensating for that this location, right? Then the head will not read data at the proper location. And it's not the same if you are using this DVD player, right? You pop a movie and you start. Let's say you can program in to accommodate for that expansion, right? And the disk doesn't have to do it real time. Well, that means that anytime you put in a disk and you're watching it from the beginning to the end, it's okay. But if you want to watch the second half of the movie, right, you go to the scenes and you skip. If it was programmed in, then it would not play right because the temperature didn't, right, reach the level, the disk didn't expand yet. So you can't program it in. You actually have to design a system that will figure out the temperature, figure out the speed, figure out everything to know how much disk expanded, right, grew in size so that this, and I mean, we're talking laser precision, right? This is not building a house where you are, like, none of the angles in the house is the right angle. You go to your house and try to find the right angle anywhere. It's construction, no one cares. It's like, yeah, it looks good, all right? It's gonna hold. So these are some of the everyday things that you see and experience, but technically any type of the design has to accommodate for these changes. And equations, you know, for this are pretty straightforward. The entire section on differentials, apart from boring problems like compute cube root of 9, is word problems where you are figuring out the change. Another one, some of you might worry about this, truck drivers need to really worry about this. Tire pressure, right? You have your rating on your tire and you want to be just below that maximum rating in the winter, and you want to relax it over the summer, right? Because in the summer it's hot outside, plus the heat from friction from driving heats tires really much, a lot, and that's why you see a lot of more blown tires throughout the summer than through the winter. Because if you go in the summer and you fill the tire all the way up and then you drive on it, it expands even more and then explodes. So we can solve a lot of application problems here. Now this book really failed in delivering. Oh no, actually here. Yeah, we have like 6. Approximate the change of volume of a sphere, approximate the change of atmospheric pressure, approximate the change of volume of the right circular cylinder, approximate the change of the volume of the right circular cone. So there are some applications that you can work on. So how about this 36? Approximate the change in atmospheric pressure when the altitude is increased from 2 kilometers to 2.1. So height goes from 2 kilometers to 2.1 kilometers. Guys, from there I immediately know that the change in height is 0.01, right? I went 0.01, I forgot the 0 here. So the change in height is 0.01. And the formula, they give you the formula in terms of the height is 1,000 e to the negative height divided by 10. That's the formula. Well, if you have that y is equal to f of x, and you say that dy is equal to f prime of x dx, now you have p equals f of h. That means that dp is f prime of h dh. I'm just changing x for h. That's, and right, y for p, x for, so just use the variables that are there. So what's p prime? it's going to be 1000 e negative h over 10 times negative 1 over 10 in the chain rule. So p prime is negative 100 e to the negative h over 10. Change in height is approximated by negative 100 e to the negative h, which is 2, over 10 times 0.01. Why did I say dh? That was supposed to be a dp. So, the change in pressure is approximately negative 1 e, negative 1 e to the 1/5. Right? Let's see what this is. E raised to 0.2. So the whole thing is negative 0.82. Does it make sense? Of course it makes sense, because the higher you go, less air pressure, right? If you are to teleport to the Mount Everest, you would pass out almost instantly because of lack of oxygen. You actually have to acclimate and take long time to train your body to operate on such a low oxygen levels. So if you are to teleport there, within 3 minutes you should pass out. You won't die, but you wouldn't be able to operate, you know, because the way you used to.
Would you be like passed out permanently, or like?
No, eventually you would acclimate. A few months.
So if you like just were passed out the whole time.
Yeah, but I don't know how the climbers who go, I don't know how long it takes them to, probably like 2 months or so, because you go from that one base to another base to another base to another base to another base, and then if you don't die along the way up, you get to spend 5 minutes on top and then make your way down. They kind of, I don't know, why would you do something like that? It takes you like 2 months, 2 months to get up, be there for 5 minutes, take some pictures, and then just go down without fingers and toes. And
well, I don't carry the auto tank.
yeah, probably. I know. Darth Vader will have no problems up there, because yeah, he will be just fine. Of course. Do not self-identify yourself that you haven't seen Star Wars, because I promise you I will never like you. Yeah, just don't. Don't be the smart person. I never seen it. Well, I don't want to see you ever again. How about that? So now you have another assignment to go home and watch the most important milestone in human development, Star Wars. You have 8 movies to see, by the way. It's gonna take you most of today and tomorrow. All right?
Have you seen Star Trek?
Yeah. And then you will do the rest of these problems the same way you're computing the change. So this is the change. Now, just to one more time iterate a little bit what's happening here. Let's talk about volume for a second. So say a volume of a cube, right? You have volume of a cube. You got offended now for Star Wars, and she's like, yep, okay, you're not gonna like me ever again. I'm leaving. Bye forever. Yeah, I talk too much. What can I say? So A, volume is A cubed. And let's say that this side A grows a little bit, right? So grows a little bit to A1. That means that the volume will grow to a volume 1, right? So if the side of the cube grows, the entire cube will be larger. And you see in which way the cube would be larger. You see that every dimension expands. So if you expand for, let's say, 2 inches, what happens to the volume? It grows 8 times, right? So if each side grows times 2, the volume grows 8 times. This is why we can't be infinitely tall, because there would be no way for our for dimensions of our body to work, right? Animals could, because they stand on 4. We stand on 2 legs. There's no way for density of the bone, the materials, for us to be much larger than this, that we actually are. We can probably grow another 2-3 inches on average as a race, but due to gravity of the planet and so on, you can look into that. But what I want to say here is exact change would be delta V, and that would be V1 minus the old V, which is A1 cubed minus A cubed. That's exact change. Approximate change, which is our differential, is dV, and that one is V prime times dA. So that's the difference between these. If you can always calculate exact change if you calculate the formula using the old number, using the new number, and subtract them. Differential is actually done to avoid that calculation, because the approximation is good enough for use, and we use it instead. Now, from here, right, looking at these equations, you go, no, it's much easier to actually compute change. But you haven't seen engineering equations yet. So hold that thought until you start working, and then check back with me and tell me which one was easier to do. Okay, great. So that takes care of linearization and differentials. We are going to stop the stream and redo this. One more section, it's short, and then we'll do other stuff later.